Good morning, everyone. I'm Homomorphic from Tsinghua University, and today I will introduce our work on faster BGP bootstrapping for POP2 cytoptomics through homomorphic NTT. And fully homomorphic encryption enables computation over encrypted data without access to the decryption key. The concept was first proposed by Rivest et al. In 1978, and the first plausible FHE scheme was designed by Gentry in 2009. Today, we have 4 generations of FHE schemes, including Gentry's original one, BGP BFA, FHE, FHE and CGTS. And there are some topics related to this work. The first one is the bootstrapping method. It allows to remove the noise in ciphertext homomorphically to enable infinite homomorphic computation. And the second one is the single instruction multiple data encoding, or SIMD. It is used by the second and fourth generation schemes to pack many plaintext messages into a single ciphertext to amortize the cost. And finally, we have to choose a cyclotomic ring for the RLW schemes, and usually the open source FHE libraries choose it to be a POV2 cyclotomic ring. And I'd like to discuss why this choice of POV2 is so commonly used. First, it enables fast and easy to implement polynomial multiplication with truly two-tree NTT. And second, it is compatible with the FHE standard. And also, using one of the latest BGP BFA bootstrapping methods from our last work on Asiacrypt 2024, when the ring dimension phi m is roughly fixed, choosing m to be a POV2 will lead to a faster digit removal process, which means a faster BGP BFA bootstrapping. And finally, when m is a POV2, the plaintext space structure will be simpler. It can be a one-dimensional or very flat two-dimensional array. And the goal we want to achieve here is BGP BFA bootstrapping that has the following properties. First, it should fully exploit the SIMD encoding property to amortize the cost. And it should also use a POV2 cyclotomic ring for the reasons just discussed. And of course, it should be efficient enough. There are several previous work on BGP BFA bootstrapping, but they cannot achieve these 3 goals at the same time. For example, the work by Chen Han at Asiacrypt 2018, they indeed use a POV2 cyclotomic ring, but their method cannot be fully SIMD and efficient at the same time. And bootstrapping used in HLib, designed by Halevi and Shope in JOC 2021, it is efficient and it supports the encoding of many messages into a single ciphertext, but it have to use a non-POV2 cyclotomic ring for the special encoding it uses. And the reasons that this goal has not been realized is that when we have a large number of slots in the POV2 ring, it means we have to use a large plaintext prime P, which makes the digit removal very slow. And this was solved by the work at Asiacrypt 2024. And the second problem is that the linear transformations will have a very large dimension. So they demand more computing time. And although there exists acceleration techniques that decompose the linear transformations into smaller and easier to compute ones, but these techniques only apply to non-POV2 rings. Decompose the linear transformations during the bootstrappings into the product of entity matrices. And because the entity matrices have only a few non-zero diagonals, they are much faster to be computed homomorphically. And this idea has already been applied to CDJS bootstrapping in 2019 by 2 papers. However, porting this technique to BGP bootstrapping faces several challenges. The first one is that the slots in CDJS always form a one-dimensional array, but it can be one-dimensional or two-dimensional in BGP and BFA. And the second one is that the entity matrices is always truly 2D type in CDJS, but it can be truly 2D or Boolean type in BGP BFA. And last one is that the linear transformations in CDJS, they operate on a scalar of complex numbers or on a vector of complex numbers or a serial vector. But in BGBFA, every slot stores a finite ring element. So the linear transformations can be viewed as to operate on vectors of small scalar vectors, and this will make them more complicated. We have also proposed some other optimizations that will be discussed later. And before beginning, I'd like to introduce the structure of the plaintext space. So with RLW encryption, we have the cyclotomic ring R2 with the modulus Q and the cyclotomic order M. The plaintext modulus is prime power P to the power of R. The ciphertext formats for BGP and BFA is given here, and I won't repeat them. And the SIMD property means that the plaintext space, which is RPR, is isomorphic to L copies of some Galois ring or field called E. And the supported homomorphic operations on this array of E include slot-wise addition, multiplication, Frobenius automorphisms, and the rotation of the slots. And to derive such a plaintext space structure, we can use the factorization of the cyclotomic ring. And we know that the cyclotomic polynomial phi mx factors into L monic irreducible distinct factors phi x modulo p when the plaintext modulus is just a prime p, and these factors phi x, they have the same degree d. So from the Chinese remainder theorem, we have the first isomorphism that the plaintext space Rp is isomorphic the product of many small rings are all isomorphic to the same Galois field. We obtain the final one, the one we desire. And in the case that R is equal to 1, R is greater to 1, the factorization can be obtained from the previous case using Hensel lifting. And now the plaintext space RPR is isomorphic to an array of Galois rings. And each of these factors, Fix, they split in E, and their roots in E correspond to a coset of the cyclic group P, a cyclic group generated by P in them star. And if we denote the quotient group of them star modulo P as H, and we pick the representatives Si as the elements in H, we can write each Fix explicitly using the SIs, and the decoding function will be just evaluating the plaintext polynomial M on different primitive roots of unity that are specified by different SI. And we will use these decoding functions later in our decomposition of the linear transformations into entity matrices. And the structure of the quotient group H will decide the plaintext space as a so-called hypercube structure. So suppose we have 2 generators in group H, and we can represent the plaintext space as a 2-dimensional array. And using the Galois automorphisms, we can rotate the elements in this array either vertically or horizontally with a arbitrary offset. And if the generators GI, their order in group H is the same as their order in them star, then the rotation can be realized with only one Galois automorphism. And we call this dimension a good one because the rotation is cheaper. And otherwise, if the order of GI in H and in them star is different, the rotations need to be realized with two Galois automorphisms, and we call the dimension a bad one. And these homomorphic rotations are important in homomorphic linear transformations. Here are some basic types of homomorphic linear transformations. The first one is the intra-slot ZPR linear transformation. It can be expressed as a linearized polynomial, which is computed by some Frobenius automorphisms. And the second type is called inter-slot one-dimensional linear transformation along some dimension S. We say that the linear transformation is one-dimensional if it acts as independent linear transformations in every hypercolumn along dimension S. And if this linear transformation is E-linear, it can be computed with just rotations along dimension S. And if it is ZPR linear, we will need both rotations and Frobenius automorphisms. And here, each of the coefficients AI or AIJ is non-zero if the i's diagonal in the corresponding matrix is non-zero. And here are some illustrations of the matrices on each hypercolumn along dimension S. We use a red block to represent a general matrix in ZPR D times D, which is just a matrix on the coefficients of each slot. And we use a green block to represent the multiplication by some element in E. And we'll continue to use the red and green for these two kinds of linear transformations later. And now we can write the linear transformations as entity matrices. So this is a typical workflow of the BGBFA bootstrapping. And we have two vectors here. The first vector is the slot vector. We view it as a ZPRN vector formed by concatenating the L coefficient vectors of the Galois ring value in each slot. And the second vector is called the polynomial coefficients vector. We also view it as the ZPRN vector of the plaintext polynomial n under the basis, the powers of x. And we have two linear transformations during bootstrapping. The first one called coef to slot. It just moves the values of the coefficient vector into the slot vector. And the slot to coef will move the values in the inverse direction. And before considering slot to coef and coef to slot, we first consider the decoding and encoding functions. In fact, a homomorphic decode function in the slots is a candidate for slot to coef. And as we have discussed previously, a decode is the composition of two isomorphisms. The first one is the CRT isomorphism, where we reduce the plaintext polynomial modulo each factor I5. And that's why we call this isomorphism red. And the representation of the same Galois ring or Galois field, and it involves evaluating each mi at some primitive root of unity specified by the representatives Si. So we call this isomorphism evolve. And evolve is an intra-slot linear transformation, which is quite cheap to compute. And for the red, it can be expressed as an iterative CRT process, where the number of CRT factors double after each iteration, and thus it is can be computed with NTT along with bit reversal permutation. And although we have an extra bit reversal permutation perm here, it doesn't really matter because the computation task between these two linear transformations is insensitive to the order of the slots. And this phenomenon was also observed in ZTS bootstrapping previously. And when the p takes the plaintext point p takes different values, the plaintext structure and the entity type will be different. When p equals 1 modulo 4, we had two dimensions. The first one has size 2, the second one has size L divided by 2. The first dimension is screwed, and the second dimension is screwed only if the extension degree d is 1. And here, each of the factors fi is a binomial, so we can have the standard related to entity here. And if p equals 3 modulo 4, we have a single dimension in the plaintext structure, and this dimension is good only if d equals to 2. But here, the factors fk, they become trinomials, so we have to use the less efficient Boolean entity. This is a toy example of the permuted red inverse when p equals 1 modulo 4 and with 8 slots. So we have three entity matrices here, n1, n2, and n3. And the first two, they are one-dimensional E linear transformations, each with 2 to 3 non-zero diagonals. And the last one is a two-dimensional E linear transformation with 2 non-zero diagonals. And in fact, these matrices, they are more than E-linear. So each entry of them not only corresponds to multiplication by something in E, that actually corresponds to a multiplication by some integer. And we will use this property in an optimization later. And here are the two examples of the entity matrices when P equals 3 modulo 4 with 8 slots. Since we use the Boolean entity here, so each entity butterfly will be a combination of 4 elements instead of 2. So we can arrange the butterfly in 2 different styles. In the first style, we call it the Boolean style. The first entity matrix will be a one-dimensional ZPR linear transformation with 2 diagonals, and the other ones will be one-dimensional E-linear transformations with up to 7 diagonals. In the second style, we call it the radix 2 style. All the matrices will be one-dimensional ZPR linear transformations with 2 to 3 diagonals. Now we can write the 12th slot and slot 12 as explicit formulas. But before that, I'd like to remark in existing literatures, the 12 to slot transformation is performed before slot to 12 in general bootstrapping, but actually we can switch their order without affecting the correctness, just as observed in ZTS bootstrapping, and that will have the advantage of performing slot to 12 at a very low modulus, which means we can compute slot to 12 really fast. And so here are the explicit formulas. When p equals 1 modulo 4, we have an extra transformation called p2n in general bootstrapping. And this is a slot-wise transformation that switches the basis of each Galois ring in each slot from the power basis to the normal basis. And this is for further unpacking operations. But using the fact that the red inverse is more than E-linear, just as we mentioned, the P2N transformations actually commutes with this red inverse. So we can combine it with eval inverse to save a level and some computation. And in simple trapping, we have an extra transformation called Rm. It will remove the extra coefficients in the plaintext polynomials. And when p equals 3 modulo 4, the formulas are generally similar to the previous case. And the major difference is that not all the entity matrices are E-linear. Depending on our decomposition style, one or all of the matrices will be ZPR linear. So the computation will be more expensive here. And another slight difference is that in the ready-to-do style decomposition in simple bootstrapping, we need an extra Rm prime transformation at last, again to remove extra coefficients in the slots. And although computing this entity matrix one by one is very efficient, but they will cost too many levels. So we use the level collapsing technique from CDS bootstrapping to combine constitutive entity matrices into a single one to save many levels, but at the cost of increasing the number of non-zero diagonals, which will further increase the running time. And from now on, we'll use the green blocks and red blocks to represent the combined entity matrices. And so, as you can see, except in the case of Boolean style decomposition, will be equals 3 modulo 4 of the product of K entity matrices is no more than 2 to the power of K plus 1. And we have also optimized the BSGS matrix multiplication. So before that, let's first look at the original BSGS. When we want to compute a linear transformation of size ds, we can choose a giant step g. The number of giant steps will be h equals to ds divided by g. And for any value I in 0 and ds, we write it as j plus gk, where j is smaller than g. So for an E-linear transformation, we can write it as two nested summation, one for a summation over k and one for summation over j. And choosing g to be roughly equal to square root ds reduce computational cost from ODS to ODS. And also we can compute multiple automorphisms on the same ciphertext faster than just computing them one by one. And our first optimization is that we can switch the order of summation over j and summation over k to minimize the number of unhoisted automorphisms in the outer summation loop. And also, the indices of the non-zero diagonals of the combined entity matrices have a very special pattern under the binary representation, just in the figure right here. So they only take several bits and leave all the other bits as 0. So we can choose the giant step g to be a power of 2, even the optimal choice square root ds is not a power of 2. And this will mean that the possible choices of the j here will be very small in some circumstances. For example, in the in his last feature, the only possible choice of j will be 0. And if you don't choose g to be a power 2, j can take from 0 to g. So combining these two small optimizations, we can have a optimized BSGS matrix multiplication for special entity matrices. During the slot to 12 and 12 to slot transformations in simple bootstrapping, the slot values will lie in a subring f of E. And so we can build the linearized polynomials on the subring instead in E. And this means we will have fewer Frobenius automorphisms and we will have faster ZPR linear transformations. And when P equals 1 modulo 4, the base ring, the subring F is just a base ring. And we can additionally omit evolve or evolve inverse. And this is the formula is given here. And the only ZPR thing here is the Rm map. When P equals 3 modulo 4, the subring F is a degree 2 extension of the base ring. And we use brown blocks here to mean that the linearized polynomials, they are built on F instead of in E. which means they are cheaper than those red blobs. And here are the experiment results. As you can see in table 2, we choose the parameters to ensure a large number of slots L, which ranges from 4,000 to about 30,000. And in table 3, we always decompose 12 slot and slot 12 into 3 submatrices. And table 4 and table 5 gives the benchmark results for thin bootstrapping and general bootstrapping. And you can observe a speed up of up to 60 times. And finally, I'd like to make a comparison with the concurrent work by Healing, published at CIC 2024. So both works use the idea of matrix decomposition to obtain faster linear transformations, but the decompositions are not the same in both works. In their paper, the Ni, they are all one-dimensional E-linear transformations with 3 non-zero diagonals. And when p equals 1 modulo 4, for general bootstrapping, both methods have the same number of non-zero diagonals, but their method require 2 more red blocks, which means our method will be faster. And for sim bootstrapping, both methods are the same, and the trace map they used here is just identical to the RM map. And when p equals 3 modulo 4, in the case of general bootstrapping, their method is better than our Redis 2 one because the number of non-zero diagonals is the same, and they have fewer red blocks. But comparison to our Boolean one is a little difficult because their method has fewer non-zero diagonals, but they have 2 more red blocks, and we need to rely on experiments to verify their performance. And finally, when for sim bootstrapping, their method is better than ours. And thank you for listening.
Thank you very much for the talk. Do we have any question in the audience? If there is no question, so I just have a short one. So you showed experimental results. Do you plan to release the code of what you did?
Yes, I have already released my code on GitHub, and I think I've.
Oh, perfect. So which library is it using?
I'm using hlib because our last word is based on hlib.
Okay, perfect. Well, thank you very much. That was a very extensive study. Yeah, very nice results.
Thank you.
So the second talk of this session, I don't know if the speaker is already online. Yes, so that will be relax functional bootstrapping, a new perspective on BGV BFV bootstrapping. And the talk will be given by Zeu Liu, which is online also.
Yes. Yes, thanks for the introduction. Good morning, everyone. My name is Zeyu Liu. I'm a PhD student at Yale. While unfortunately I'm not able to give this talk in person, I'm still very excited to be here, at least remotely, to talk about our work, Relaxed Functional Bootstrapping, a new perspective on BGV and BFA bootstrapping. It's a joint work with my colleague Yunhao Wang. So of course, hopefully you will enjoy this talk. Also, due to the time limit, I will need to skip a few slides, but I keep them inside. And if you are interested, they're available on the Asiacrypt website, and you can check them. And I'm definitely more than happy to take questions through emails as well. Okay, so let's get started. I believe most of you are already familiar with FHE and bootstrapping, especially after the first talk. But for the sake of the self-containment of this talk, I would still like to give a quick background introduction. So suppose we have some data, X, and we can encrypt them under FHE, and then we'll obtain some ciphertext encrypting this data, X, and then we can evaluate. This allows us to evaluate some function F over the ciphertext, and then we'll obtain some new ciphertext encrypting F of X. And for all the existing FHE schemes, there are some initial errors. So after you evaluate this function f, the error basically accumulates. And after this error accumulates to some point, if you want to perform some further operations like f prime, instead of getting what you expect to get, you will get some random noise. So this is not possible. How can we do if we want to evaluate this f prime? What we can do is we can perform this procedure called bootstrapping. And this bootstrapping will basically, it will not change any of the content in the ciphertext. The content of fx remains, but the noise will decrease by some amount. So after it decreases to some threshold, you will be able to further evaluate what you want, like f of prime, and then f prime, and then you will get encryption of f prime of fx. Okay, this sounds amazing, but there's one caveat, is that the bootstrapping procedure itself is very inefficient. Okay? It is inefficient for two reasons. The first is that bootstrapping circuit is quite complicated. Probably you can see it from the first talk already. And the second reason is that bootstrapping basically itself does nothing else. What do I mean by that? I mean, basically, as I just mentioned, it doesn't change the content. So if you want to evaluate some f prime, it means that you need to wait for this bootstrapping procedure to finish without doing anything else. So in our work, we define and build this concept, what we call a relaxed functional bootstrapping. And the great part of this relaxed functional bootstrapping is that first, it allows us to build some more efficient bootstrapping circuit. So itself is faster. And the second is that it allows a free function evaluation during bootstrapping. So you don't need to wait until the bootstrapping itself to finish. It itself will help you do some additional work you want. Okay, so
excuse me, we have a technical issue that the slides disappeared.
Wait, sorry, I can reshare. Let me see if that helps.
I think it's on our side.
Can you see it?
Not yet.
Okay, then yeah, I guess it's not at my side. Okay, I think yes, you can see it. Great. So yes, let's continue. As I just mentioned that, so our work we define this relaxed function bootstrapping. The first allows more efficient bootstrapping circuit, and second, it allows a free function evaluation during bootstrapping. So itself is not wasteful anymore. Okay. Okay. So again, I will introduce some background about BGV BFE. First, it is a ring LW based. It works over this ring z of x over phi n of x, and this phi n is the nth cyclotomic polynomial. And the ciphertext has this form AB, which are just two ring Q elements. When I say ring Q, I just mean that if the elements are in the ring represented by polynomials, all the coefficients of these polynomials are in ZQ. Okay. And then it satisfies B equals to AS plus E, where this S is some secret ring element and E some small error, and plus some encoding of this message you want to encrypt M. Okay, and this message M is within this plaintext space ring of P to the R for some P to the R. Yeah, this message is in this. And then so there's a special kind of parameterization. Suppose this n is a power of 2. And it satisfies that p mod 2n equals to 1, then we can view this plaintext space to be z of p to the n. So it's a vector of length n, a vector of zp of length n, instead of just a ring p element. Okay, so why is this important? We believe for lots of works that this kind of for lots of applications, this kind of parameterization will give you the best performance. So throughout this talk, I will be focusing on this kind of parameterization. And BGV BFA allows majorly allows addition, multiplication, and they are working over this vector zp to the n, and the operations are element-wise, and these are just two illustrations of the element-wise addition and multiplication. Throughout this talk, I will basically assume everything is done element-wisely, and you will see. Okay. For most of the past works and also some concurrent works, they follow this paradigm. Of course, I don't expect you to read or understand. The only thing I would like to emphasize is that most of the works require this kind of a procedure which they temporarily enlarge this plain text space from p to the r to p to the e for some e greater than r. This basically restricts some choices of p, which sort of reduces like the efficiency of the past works, and we do not have this. Okay. With all this in mind, before we dive into the constructions, let's first take a look at what the definition of our relaxed functional bootstrapping. So what do I really mean by relaxed functional bootstrapping? Okay, so first, as mentioned, we work over this plain text space zp to the n, a vector of a zp of length n, and everything is operated element-wisely. And then we require that the correctness, we only require the correctness to hold for some subset x for some set x that's a subset of this zp. Okay, so it means that if the input message m is within this valid input set x, then the output should be f of m for some predefined function f. And okay, what about otherwise? So we'll talk about that in the next slide. And the second requirement is that we require the output noise budget to be greater than the input noise budget. So this is the basic requirement of the bootstrapping. Of course, if the function f is non-trivial, then it can also be interesting even if the noise budget does not increase. But for the sake of this talk, we will not go through that direction. And lastly, I'd like to mention that regular bootstrapping is indeed a special case of ours. If you just look at the definition, if you just let this subset x be zp itself, and you let this f be an identity matrix, this will be a regular bootstrapping. Okay, so after you hear this kind of definition, you may ask, why is this reasonable? Why we only need to guarantee correctness for a subset instead of the entire plain text space? Well, we believe that for lots of applications, we know the input to the bootstrapping circuit in advance. What do I mean by that? Let me first give an example. So for example, if you have a comparison circuit, after you get a result, you would like to bootstrap this result. But you will know in advance that this result will either be 0 or 1, indicating like it's greater or smaller, something like that. So in this case, you do not need to worry about other kinds of inputs. And the second example is that for some applications like PRR or PSI, we can sort of encode the data in advance. So we can encode this data to be within this set X instead of this ZP. At the end of this talk, if we have time, I do have a small example, but this is indeed one application, very important application we have in mind. So with this, hopefully I can convince you that it is reasonable to only guarantee some partial correctness. And this is our formal definition. I don't expect you to read. I just like to emphasize two things. The first is that this is the first requirement. Only if the input is valid, we require the correctness to hold. And the second is that we require the output noise budget to be greater than input noise budget. Okay, so as just promised, what happens if m is not in this valid set? Okay, so in general, we actually do not care. So this is the core source of our efficiency improvement, because we don't care about those parts, and so we can get some efficiency improvement compared to prior works. However, we do define some additional property which we call L closeness. It basically means that this input m, if it's not in the valid input set, will output f m of m prime, where this m prime is indeed in this valid set x, but it's not m itself, but it is one of the L closest elements to m. Okay. Some of our constructions achieve this property for free. Some achieves it with some costs, and some just do not achieve it. Again, this is not really the main point of this work. We just include this definition because it can be useful for some applications like privacy preserving machine learning. but it can be like not useful for some other applications. Okay, so else closeness definition is as follows. I would just like to emphasize here. This defines that the L closest points. Okay. So with all this definition in mind, we can talk about our constructions. Our starting point, we first give us a simple subset. This subset is structured. It has this following form. It starts with 0 and it ends with p minus 1 p, minus r. Recall that p is the plain space, and this it has some step size r. It basically means 0r, 2r, 3r up to p minus 1 minus r. Okay, this r is something we will define later, but it's just some parameter. And then also we assume r divides p. Actually, r divides p minus 1. Sorry. And otherwise, we can just choose r to be the nearest value that divides p minus 1. Alternatively, we can also define 0 to p minus c minus r for some integer c such that r divides p minus. Okay. And then lastly, we define this function f to be our identity function. So you can see this kind of special, this case is like a strictly weaker than a traditional bootstrapping, because we only work over this subset, and this function, we define this to be identity function. Okay. And again, we output m if m is in X. It's the definition of that identity function. Okay, this is the illustration of our valid set, which is 0r to r up to what I just explained. Okay, so with this, we give our construction. How can we bootstrap this this special kind of subset? So given some ciphertext A, B in this ring Q, both of them are ring Q elements. They are encrypting M, a single message M in ZP. Again, the plain space is a vector of length n, but we only look at a single element at a time because it works exactly the same for all elements, because every operation we are doing is element-wise. Okay. First, what we do is we module switch this ciphertext to some A prime, B prime that's in ring P. Okay, you can see this ring P is the same as this P in the plain X modulus, and now it's encrypting some M prime in ZP. Sorry for the typo. So it's now encrypting M prime instead of the original M. Okay, what is this M prime? If this M is within this valid set X, then M prime is within M minus 2 to the R, and m plus 2 to the r, and this r is some modular switching error. Okay, so this is where we define this r. This r is some modular switching error, satisfy this condition. So basically, if the elements are in this valid set, it will be mapped into one of the ranges of the ZP, one ranges among this ZP whole ZP range. Okay, for example, 0 is mapped to 0 plus 2 r over 2, or 0 minus r over 2. Okay, so then what we can do is that after obtaining this new ciphertext A prime B prime in ring P, we can try to homomorphically decrypt it. We compute this minus AS plus B in this ring P. Okay, this can be done easily, and we will not cover it in this talk. This can be either done through linear transformation, homomorphic NTT, something similar to what you heard from the first talk. And then after we obtain this gives us the encryption of M prime. So what we do next is we will compute this function we call fpost, post-processing function. And this function will map this range M minus 2 to the R to M plus 2 to the R, this range back to M for all M in this valid set. Okay, this can be done via degree P minus 1 function, and this is the illustration. You can see it's very similar to the last illustration. The only difference is now the modular switching is the changing from this to this, and the fpost is mapping from the range back to a single point. Okay, so the correctness is achieved in a straightforward way. We're just doing the process backwards. It achieves two closeness because so if M is not in this X, it will basically be mapped. Suppose it's between R and 2R, it will basically be mapped back to either 1 or 2, either R or 2R. So it's one of the two closest points. Okay, so this is our starting point. Yes, and then with this in mind, we can do something more complicated. So let's now define the X to be less structured. Of course, it's still structured. Now it starts with the point U and ends with point V with some step size R prime. That's not the same as the R, which is the modular switching error we just mentioned. And this R can be arbitrary. Okay. The only requirement we have is that the size of this x2 is at most the same as the size of x1 we just mentioned in our previous slide. Okay. Now we don't define f to be an identity function. We define this f to be an arbitrary function. So it can be any function you want to evaluate from x2 to zp. And it means that if m is in this valid set x2, you will output f2 of m. Okay, this is the illustration of x2. They are now you can see different from x1, but they still have this structure that has a fixed step size r prime. Okay, so what we do for this is now first, the issue with this is that now it's possible that r prime is smaller or equal to r. So it means that the modular switching can cause some error. So what we do is that we will first compute some homomorphic function, pre-processing function, homomorphically we call f pre, and this f pre will just map this x2 to the x we just mentioned. Okay, so we do this mapping. And this mapping can be done via this function. This function only requires one level of plain text multiplication, and furthermore, it can be merged with slot2 coif, so it essentially can be achieved for free. If you are not familiar with slot2 coif, well, first it's probably means that you did not attend the first talk, but more importantly, it doesn't really matter. The point I want to mention is that basically this f3 can be evaluated for free. Okay. And then again, after we get this, we will perform modular switching and homomorphic decryption as in the previous slide. Of course, now we need a new post-processing function because now f2 is no longer the identity function. Also, we need, even if it is, we need to map back to x2. Okay, so f post 2 can be just this function. It's a bit complicated. I will not expand, but the point is that it can also be interpolated with just a degree p-1 function. So it will cost essentially the same as the first starting point we discussed. Okay, so with all this, we can conclude and say that this is our general framework. We have this ciphertext input. We will evaluate some function f pre-processing, and then we'll get some output, evaluate the slot2 coif. Again, it doesn't really it's not important for the sake of this talk. And then we perform modular switching, homomorphic decryption, and evaluate some function f post at the end. Okay. So this is the general framework we have. And with this framework, we'll be able to build some more fine-grained constructions. But all these constructions, for the sake of time, I will skip the details. I will just talk about what they are. For example, you can define some more arbitrary set. This set no longer has structures. It's just y1 through yz. And it's just arbitrary points. We only require that the number of points is smaller or equal to the set we just defined. Okay. And again, this f3 can be an arbitrary function. And again, as just mentioned, I will skip the details, but this is one thing we can achieve. This is one thing we can achieve in a more fine-grained way. Okay. Then we also can achieve something we call ranges. Okay, so if the input valid input set it contains k ranges, and these ranges are well separated. So what do we mean by well separated? We mean that the difference between vi and uj is at least greater than this r. R is the modular switching error. So in illustration, it looks like this. All the ranges are this dark gray ranges, and this light gray ranges. This light gray part is indicates that they are at least separated by r points. Okay. And then the function f4, it can be an arbitrary function that maps one range to one point. So it cannot be point-to-point functions, but it can be mapping any range to any point. Okay. So in this case, we'll also be able to achieve something that's more efficient than what we described before. But again, I will not talk about the details. And lastly, I want to mention we can achieve is what we call unbalanced ranges. So suppose we have only two ranges, and one, of course, they are again well separated, but one is being a lot larger than the other. Then in this case, we can do it more efficiently than the previous case. Of course, it can be extended to k ranges, but preferably with one range that is much larger than all the other ranges combined. Okay, I'll skip our construction. I'll directly go to benchmarks. If you take a look at this table, so if you consider the per bit runtime compared to prior works, we with a similar security guarantee, more than 120 bits, we can achieve two to three orders of magnitude improvement for the per bit throughput. This one has, even for this one that has only 66-bit security, we can also achieve like more than one order of magnitude for some function families. So if you decompose our construction, you will see that the total runtime and this lookup table evaluation runtime is the runtime for the post-processing function. So for some function families, those F1, F2 are the two starting points we just discussed in detail. They are close to taking most of the time. But for some other function families we just mentioned, they are more fine-grained, and the lookup table runtime is much smaller than the total runtime. So it means that there can be some potential optimization possibilities. But anyway, as you can also see in this table, compared to prior works, we improved by two to three orders of magnitude. Okay. Okay. As promised, I will mention some applications very fastly because the time is limited. So what we can do is something is called oblivious permutation. So in this work, they propose a way to do homomorphic permutation. It basically means that given a database of n bits or n entries, the server will randomly permute it without knowing the exact permutation. Okay, this is done via a Thorpe shuffle, and then using some random bits encrypted under a sheet. I will not talk about what Thorpe shuffle is. If you can follow, you can take a look at this animation. And basically, after this process, you will get a permutation, but it's not random, so you need to repeat this Thorpe shuffle process for k equals to O lambda times. And this will give you a random permutation except with 1 minus negligible probability. Concretely, this k equals to 400, which means that it at least requires 400 levels. And this means, and for simplicity, assume that the bits used to permute are just easily sampleable from FHE, and this is done in this work. I will not expand, but the point is that this is very suitable for our relaxed functional bootstrapping because first, it requires 400 levels, and second, because it is permuting some database elements, it means that we can first encode the database elements into this valid set X, and then the permutation circuit will only involve swapping, although I did not expand, but it will only involve swapping, which means the elements will not change. So the input and output will both within this X. And using our bootstrapping, the runtime can be 100 times faster than using prior works for the bootstrapping part alone. And we have some extra benefits to allow, say, more slots, more free parameter choice, which can make it more efficient. Okay. There are some other applications we discussed in our paper. I will not mention it in this talk. And that's pretty much it for the talk. There are lots of interesting open questions, and this is the link for our paper. Thank you all very much for listening. I can now take questions.
Thank you very much. We have time for one short question. So is there a question? Yes. All right.
Is anyone talking? Sorry, I cannot hear anything.
Yeah. Thank you for nice talk. Just have a short question. Can you show me the benchmark table again?
Yes.
Then,
This one?
then what is? No, the next table.
Okay. Yes.
What is F1 and F2 here? My
Right.
understanding yeah, just What is F1 and F2 here?
Yes, F1 is the first set. So the first function family we described, F1 is just a subset, and this function F is the identity function. So that construction. And F2 is the one that we have less structured, but still have a fixed set, fixed step size input set. And then we have this function to be arbitrary function. So those are the two constructions we described. Yes.
Yeah, it seems to me natural that that special functions like f points or f range, that how they can be faster than f1 and f2.
Yes. Okay. Yes. Good question. So, for example, for f points, the input set may be smaller, right? So, for example, for f1, f2, the input set can be say 500 points, and for f points, they are like say 8 points. In this case, it's smaller. And for f ranges, it may contain also 500 points, but they are mapped as range. They are arranged as ranges instead of individual points, so they can also be evaluated faster in some faster way, and similarly for some unbalanced ranges. So,
Okay, thank you.
yes.
Yeah.
Well, thank you very much for the talk. Let's thank the speaker again.
Thank you.
And now let's move to the third and last speaker of this session. So the paper is called Entry-based bootstrapping for multi-key FHE without using overstretched parameters. And the speaker will be Binwoo Hyang.
Okay, can you hear me?
Yes.
Okay, thanks, Rintra. I'm Bingwu. Today I'm really excited to be here to introduce our new work, Entry-based bootstrapping from multi-key FHE. This work was a collaboration with Dr. Jiang Zhang, Kaixin Wang, Yi Deng, and Deng Guofeng. First, let's review some basic definitions. The FHE, as the holy grail of cryptography, allows arbitrary operations on ciphertext without declarations. As shown in the example above, consider the ciphertext of two numbers 6 and 3. When we perform addition and multiplication on this ciphertext, we obtain the result, and when decrypt give us 9 and 18, and the result is equivalent to perform the same operation on the plaintext. FHE also has many applications, including PPML, PIL, PSI, and MPC. However, traditional FHE only supports computation under a single key, making it unsuitable for multi-key situations. Therefore, we need multi-key FHE, which allows the homomorphic computation under different keys. And it's worth noting that unlike threshold-based schemes, the key generation and encryption don't require the interaction, but the decryption still require the distributed decryption. Moreover, the time-space complexity is typically related to the number of the keys. And currently, most multi-key FHE schemes are based on LW or ring LW, and the majority are still theoretical results without code implementations. And there are two types practical schemes. One is the worldwide schemes, CKS and BFA. Both are naval FHE. And the bitwise the schemes, multi-key TFG schemes like CCS and KMS, both with gate bootstrapping. But the first multi-key FHE schemes LTV is indeed based on N2. So why have there been so few schemes based on N2 since then? Okay, let's review the real dummy and untrue assumptions. Real dummy instance consists of two ring elements where B is equal to A times the secret key S and plus the noise E. And an untrue instance consists of only a single ring element C, and C is equal to G times the inverse of F. Here, F is a polynomial with small coefficient and usually simple from uniform ternary secret distributions. So in Tiffany, NTRU ciphertext only a single ring elements. So constructing schemes based on the untrue assumption seem to nature offer advantages. And the early work, such as LTV, was based on untrue and actually more efficient than the corresponding real W-based schemes like BGRay. However, the LTV schemes, the noise grows exponential in the number of parties and the number of homomorphic operations. So, in other words, the model scale for the LTV schemes must be exponential enough to control the noise. In Asia 2021, Dukes et al. Studied two types of NTRU attacks, K-recover attacks and the subnetted attacks. Also, through their experiment, they found a vertical point where Q is equal to the O to the power of 2.484. And when the models beyond this point, the subnetted attack become more effective. Therefore, in the LTV schemes, as soon as the king extends a small constant, it will surpass the vertical point. So our goal is to design an NTRU-based multi-king schemes that support a large number of kings or parties. Current schemes face a major problem is that their exponential noise growth. To solve this question, we introduced an NTRU-based multi-key schemes that allows us to work with sublinear keys and without using the NTRU parameters. We follow the two-layer framework in MKTFHE. In the first layer, we use a matrix entry-based encryption that supports multi-key net operations, and our model Q is only O of the k times the n to the power of 1.5. As you can see, our model's Q is linear in the k. Our second layer also entry-based encryption that supports the Haber product for gate bootstrapping. And we can use our entry-based second layer bootstrapping to bootstrap a multi-key LW ciphertext. Finally, we also introduced a new LW to LW key switching to reduce the key size from ON squared to ON bits. Now, let's look at how the first layer matrix entry-based multi-key encryption is constructed. In the setup files, each party I samples an inversible matrix F as their secret key and also generates a fresh ciphertext of 5/8 of Q for evaluations. And then each party then encrypts their 1-bit message like this. The security of this ciphertext relies on matrix entry problem. Here, the matrix C is equal to the matrix G times the inverse of F. And this matrix C is computational integrable from a uniform random matrix. Also, we need KDM assumptions. And as you can see, our ciphertext only contain n-dimension vector, so we actually only use the first row of the matrix C to define the ciphertext. The multi-key ciphertext is formed by combining the ciphertext for all parties, and the secret key is also a combination of everyone's secret key. And to decrypt, we just compute the inner product between the ciphertext vector and the first column of the secret key matrix. So when it comes to the multi-key homomorphic net operations, we first extend the single key ciphertext by padding with 0 to create a multi-key ciphertext. For example, when there are two parties, we can extend the ciphertext C1 to C10. In fact, the C10 is a multi-key ciphertext under the secret key F1 and F2. Then we only perform a linear combination of the extended ciphertext and output the result of the net gate computation. Next, let's introduce how we performing the bootstrapping for this matrix-based untrue ciphertext. We first construct a new untrue-based hybrid product that allowed us to achieve the homomorphic multiplication between a single key unique encryption ciphertext of mu I and the multi-key untrue ciphertext of mu. Then output a new multi-key untrue encryption of mu times mu I. But as you can see, both the public key and the unique encryption ciphertext for party I are designed to using the same secret key as, so the above construction rely on a new assumption called hint untrue assumptions. Also, as discussed in one paper in Asiacrypt 2024, Hassian syntactic signature schemes with a suitable choice of secret and error distribution, the hint untrue problem is at least as hard as the standard untrue problem. After k-n iterations, we obtain a multi-key untrue encryption of this. Here, the Rx is a polynomial where we specially designed the coefficients so that the constant of the ring ciphertext is exactly what we want. Then, we also propose a key-switching method to convert the multi-key untrue ciphertext into the first layer multi-key untrue ciphertext for further operations. This is our two-layer workflow consist of a first layer matrix untrue based schemes support multi-key net operation, and second layer is bootstrapping contains the blind rotation and key switch. In fact, we can also use the second layer of untrue-based bootstrapping to bootstrap the first layer multi-key LW ciphertext. The only difference is that the output of the blind rotation is a multi-key untrue ciphertext. Therefore, we need to use a simple extraction to obtain a multi-key LW ciphertext, and then apply the key switching to switch back to the first layer ciphertext. However, it's important to note that the key switching step typically requires storing a key size of 100 MB. So it becomes the most heavy storage cost in the bootstrapping. To solve this question, we also provide a new key switching method. Let's review the previous approach. The input is a LW ciphertext like this, consists of B followed by A1 through AK. Here, each AI is n-dimension vector space over ZQ, and the goal is of the key switching is to switch the secret key from a k big N dimension secret key back to a k small n dimension secret key. To achieve this, the previous method involved enumerator or possible decomposition of the elements as in some basis B, and then storing all of the values using the LW ciphertext. In our approach, we pack big N LW key switching keys into a single ring LW ciphertext, and for the key switching, we only extract almost free coefficients using the index, and this method also applicable to single king LW to LW key switch. As a result, the key size is reduced about 100 times, and theoretically speaking, we reduce the key size from ON squared bits to ON bits. It's worth noting that the secret key after the key switching is only of length small n. So while our real W key switching key is in big N dimension space, this means that the secret key in our key switch key only has value in the first n entries. Theoretically speaking, as long as the secret key has sufficient entropy, it can still be reduced to the standard ring LW assumptions. And in practice, when we choose our concurrent parameters, we can treat the ring LW ciphertext into big N samples of LW instance in dimensions small n instead of the big N for a standard ring LW instance. And we have actually taken this into account when choosing our concurrent parameter using the LW estimate. And here is our comparison between ours and the existing NTRU-based multi-king FIT schemes. And as you can see, in traditional and true-based multi-king schemes, the noise grows exponential with respect to both the lattice dimension and the number of parties k, and then to the need for large models. And when the parties beyond 2, the model size in these schemes will beyond the fatigue point. In contrast, our schemes use a much more efficient approach with a model size of Q equal to OK times the n to the 1.5. Thus, we can choose our k equal to n to the 1.9, and our parents also can beyond the fatigue point. In this table, we provide an experimental comparison of our schemes with other ring LW-based multi-K TFHE schemes. And also from the table, you can see that our multi-K FHE schemes are faster and has small bootstrapping keys than previous. For example, when the key number is 8, our scheme is about 2 times faster than both KMS and CCS. Moreover, the key size in our schemes is 7 times more than CCS and 18 times more than KMS. Also, it should be emphasized that all the results are from single core runs, and the KMS schemes is actually better than ours for multi-core parallel because they are better suited for parallel situations. Okay, overall, we introduced a new intro-based multi-K FHE, and without using the overstreet parameters, and also with fast bootstrapping and small key size. What's more, our intro-based multi-K FHE is the first one to support a sublinear number of keys. And thank you for your attention. Our code is already open source, and you can find it at this link. And if you have any questions, feel free to ask me.
Thank you very much. So do we have a short question?
Hello, hello, Bing.
Hey,
Can you hear me on Zoom?
Yeah, I can hear.
Okay. I have a question. So, what is the main difference in design between your work and the previous intro-based work?
Okay. In my opinion, the main difference is that the previous intro-based schemes like LTV generates their multi-key ciphertext by directly multiply their single-key ciphertext, so that their ciphertext length is constant, but their noise grow exponential with the party's number. However, our approach follows the two-layer framework in multi-key TFT. The first layer is the first layer only achieve a simple net operations, so the noise grows linear in the number of keys. And our second layer also use the intro-based GSW-like schemes, so the noise growth also is a Coulson addition noise growth. Thus, our pairmates can control under the fatigue point, but our multi-key ciphertext is growing linear with the but our multi-key ciphertext length is growing linear with the party number. Okay, I think that's the main difference.
Okay, okay, thank you.
Okay, so let's thank the speaker again and all the speaker of this session also.